What's up, people? Let's move on with particle nature of electromagnetic waves or electromagnetic radiation. So, we discussed a prelim round of the particle nature electromagnetic waves, and we discussed that this energy or this radiation is transferred in the form of photons having an energy of mc square, where m is the mass of the photon and c square is the speed of light. C is the speed of light, and this energy is also equal to h mu, or the Planck's constant, into the frequency, where the Planck's constant is 6.626 into 10 raised to minus 34 joules per second, or it can be also noted in the form hc by lambda, where lambda is the wavelength of the radiation or wavelength of the wave. Now let's have a detailed discussion of the particle nature of the EM wave, and this can be easily done if we look into two biggest experiments that led to this particle nature of electromagnetic radiation. And this particle nature of electromagnetic radiation in all is called the Planck's quantum theory. So we must have heard about the word quantum a lot of times, but the basis of this quantum theory is based on two big experiments by two named scientists. Some of the experimental phenomena, such as the diffraction or interference, where diffraction you can say is a bending of light, about an obstacle. That is, if like say that I have an obstacle like this, and I have light passing in this direction. Let's say I have light passing in this direction, then this light can go above this obstacle due to diffraction if the obstacle thickness is in the range of the wavelength. So this is called diffraction. In the same way, there is interference. Interference is when two waves of same or different frequencies combine and give, let's say, a resulting wave. So what I'm saying is, right, that if let's suppose that I have a wave like this that is coming here, and another wave is coming in this direction, then at this point where they meet, there will be an interference pattern, and this will lead to let's say it will lead to a resulting wave, which will be a vector result of these two waves, and which is a physical topic, but it is called interference. And when two waves interfere with the pathway of both of them, they result into another wave due to the vector sum of disturbances at this point, and thus form an interfering wave. Right. So this is diffraction interference, and this could be very well explained by the wave nature of electromagnetic radiation, because electromagnetic radiation also gave these phenomena like diffraction interference. However, there were some observations in the late 19th century which could not be explained using wave nature, or neither could be explained by classical physics. Okay, the first one was the nature of emission of radiation of hot bodies or black body radiation. So what actually was happening, that we have, let's say, this thing here, then this thing emitted some kind of radiations. Okay, these were called black body radiations, and when these observations were taken about this black body radiation, they were not at all mixing or resulting into the wave nature of electromagnetic radiation. Okay, so this is one of the observations that were given in the 19th century. The second was the ejection of electron from a metal surface. Like for example, if we had a metal surface like this, then if radiation was shown on this like this, then electrons started to eject out of it. When the radiation struck away, and this was called the well-known photoelectric effect, which is the basis of all type of solar energy that we have. So this is called the photoelectric effect. Okay, the photoelectric effect. The third was the variation of heat capacity of solids as a function of temperature, which is also a part of the black body radiation only. And the fourth and the very important one was the line spectra of atoms with special reference to hydrogen. The line spectra of atoms actually meant that in the case, like for example, I have uh, this let's say atom here, and let's suppose right now that it is a let's say this is just a ball or a ball of atom. We don't know that how the atom looks like now. So what is happening here is that if I like if I what I do is I like put some light on it, like radiation is falling on it, and I put a piece of paper on the back of it. Then what was happening here was that there were certain lines on this. Okay, there were certain lines on this. Let's say like this, I have one line and a lot of line like this, which is called the spectra, the absorption or the emission spectra. We can call it a spectra or a spectrum. Okay, this is called the spectra. So when light fell on it and when light came out of it, it led to a spectra which was not well expected as per the wave nature. So this was also found out in the late 19th century. Therefore, it was important that a second theory needed to be applicable in order to explain all these three or all these four kind of observation. And the first concrete explanation for the first phenomena, the first black body radiation, was given by an eminent scientist, a well-known scientist called Max Planck. It is the story behind Max Planck that one day Max Planck was about to give a lecture. Was about to give a lecture on one of this black body radiation only, and one of the guards did not know him, or one of the professor guards. Actually, the guards were a professor, and they were seeing the invitations of the people who used to come in there, and he was looking at the invitations. So Max Planck came in, but he did not have an invitation. So he first of all, rather than looking at the invitation, he looked at Max Planck, the professor guard. He looked at Max Planck and said that you do not have the potential to sit in the great eminent Max Planck's lecture because you're too young to understand it. Because he didn't know who Max Planck was, but he had heard that Max Planck was an eminent scientist, and his words of wisdom were like were the basis for scientific phenomena to happen. And but to his lack of knowledge, he did not know that Max Planck was standing in front of him. So it says that in a very young age, Max Planck had put himself into the scientific world as one of the most eminent scientists ever. And he was the one who put forward the biggest quantum theory on which the quantum physics is based on. So it was Max Planck who gave the first concrete explanation of the phenomena of black body radiation. Okay, so we'll just discuss a short, give a short explanation of the black body radiation or the quantum theory given by Max Planck. So what actually was happening here? When we talk about Max Planck quantum theory, we need to discuss about radiations, and we know that in case like if I have this ball and I start to heat it, I put heat and I start to heat it, then then it starts to emit kind of radiation. Like if we keep a iron rod, let's suppose that we have we have an iron rod like this. Yes, we have an iron rod like this. Okay, so we have an iron rod and we are starting to heat it, and we know after some time it starts to become red. Right, it starts becoming red, and after some time it starts becoming blue. If we heat it more, it will start becoming blue. It starts becoming blue. After some time, you will see it turns colorless, right? And that is the end of like these are the sequence of radiations that take place. So what actually is happening here, if you understand, then we know that light is a type of electromagnetic radiation, right? So light is a type of electromagnetic radiation. I will denote it by EMR. It is a type of electromagnetic radiation, and what we see colors is also light. So what is happening here was that the as it was being heated, more and more heat was given, different type of light was coming out, and it was also found out that these lights had different frequencies and wavelengths. So the red, blue, etc. had a different frequency, and let's say yellow had a different frequency had different frequency or different wavelengths. Okay, so what is happening here was, in terms of frequency, it means that when it was heated, the frequency of the emitted radiation, let's say we have this frequency, it goes from a lower frequency to a higher frequency as the temperature increases. So as the temperature was increasing, the frequency was also increasing, and the red color lies in the lower frequency region, while the blue color lies in the higher frequency region of the electromagnetic spectrum. Okay, so what was thought about is that it behaves like a black body. So what actually is a black body? Like if we have, let's suppose like a body like this, it is completely black, then it is said that this black body is a very good absorber as well as an emitter. Black body is a very good absorber and emitter, and the radiation emitted by such a body is called black body radiation. So you just need to know about this about black body. The main purpose here is that why did the radiation depend upon the frequency rather than the intensity? If you look at the intensity versus the frequency curve, then it was like seen that at a certain temperature, the intensity varied with the wavelength, and at a certain wavelength, the intensity was highest. Like the wavelength, the graph looked like something like this. Let's suppose, let me draw it in a new page. Like I have this, and this is intensity denoted by I, and this is wavelength lambda. So what was happening here was that at, let's say, sub temperature T1, the graph looks something like this. At some temperature T2, the graph something like this. Okay, and it was seen, this is at T2, and it was seen that T2 was less than T1. So that was not, this is not very important, but the main concept here is this thing, that there is certain high point at certain wavelength. Okay, at a given temperature, the intensity of radiation emitted increases with decrease of wavelength, reaches a maximum value at a given wavelength, and start decreasing with further decrease of wavelength. The above experimental results could not be satisfactorily explained by the basis of wave theory of light. Thus, at last, Max Planck suggested that atoms or molecules could emit energy only in discrete quantities, and he gave them the name quantum, the smallest quantity of energy that could be emitted or absorbed. And he also found out that this energy was proportional to the frequency, and thus when we remove the proportionality symbol and put forward the equality symbol, we have a proportionality constant h, and this h is called the Planck's constant and has a value of h is equal to 6.626 into 10 raised to the power minus 34 joule second. With this theory, Planck was able to explain the distribution of intensity in the radiation from black body as a function of frequency or wavelength at different temperature.